What if I told you that particles behave differently when you're watching them? It sounds like science fiction, but this bizarre reality sits at the heart of quantum physics, the strange world where the mere act of observation changes what happens. Like a chameleon changing color when spotted, in the famous double-slit experiment, light particles create a wave pattern when unobserved, but switch to behaving like ordinary particles the moment we try to watch them. This phenomenon has been rigorously verified in laboratories worldwide, fundamentally challenging our understanding of reality. The implications reach far beyond physics, forcing us to question whether objective reality exists independently of our perception. The centuries-old physics debate, waves or particles. What if the greatest minds in physics spent centuries arguing about something that turned out to be both right and wrong at the same time? That's exactly what happened in the debate about the fundamental nature of light. Two brilliant scientists, Isaac Newton and Christian Huygens, stood on opposite sides of a divide that would shape physics for generations to come. In the late 17th century, Newton proposed that light consisted of tiny particles he called corpuscles. These minuscule bits of matter traveled in straight lines at incredible speeds. His famous prism experiments provided compelling evidence by showing how white light broke apart into a rainbow spectrum when passed through glass. This separation aligned perfectly with the idea of different colored particles, each with slightly different properties. Newton meticulously documented these particle streams' behavior. When they encountered glass surfaces, some bounced off while others penetrated, creating both reflection and refraction. Particles entering glass changed direction because, as Newton reasoned, the glass exerted an attractive force on them. This explanation complemented his groundbreaking work on gravity and motion, forming a coherent mechanical model that explained phenomena from shadows to colorful soap bubbles. In contrast, Dutch physicist Christian Huygens championed a completely different theory across the English Channel. Huygens proposed that light traveled as waves through an invisible medium called ether that permeated all space. Light sources created disturbances in this ether similar to ripples spreading across a pond after dropping a stone that propagated outward at light speed. Huygens' wave theory offered its own compelling evidence. It elegantly explained reflection and refraction as waves bouncing off surfaces or changing speed between materials. When light passed from air into water, the wavefront slowed and changed direction, exactly matching observations. The wave theory also predicted that light should bend around obstacles slightly, creating fuzzy edges rather than the sharp shadows Newton's particle theory suggested. With both theories supported by strong evidence and brilliant minds, the scientific community divided. This division had practical consequences beyond academic circles. Naval officers plotting nighttime maneuvers found their signal lamps behaving in ways that sometimes aligned with wave predictions and other times with particle expectations. Telescope makers discovered that certain lens arrangements worked better than Newton's theory predicted, while microscope designers struggled with diffraction limits that matched Huygens' calculations. Newton's particle theory initially dominated largely due to his towering reputation. When your opponent has essentially invented calculus, discovered universal gravitation, and revolutionized mechanics, challenging his conclusions requires extraordinary courage. Yet the wave theory persisted because it explained phenomena that troubled particle theorists, particularly diffraction, light's tendency to bend around obstacles. When light passes through a small opening, it spreads out in patterns indicating wave behavior rather than forming the perfect beam particles should create. For over a century, this fundamental disagreement divided physics. Increasingly sophisticated experiments were conducted, with each side interpreting results to favor their preferred theory. The question became a defining choice in a physicist's career. Are you a particle person or a wave person? The practical stakes were enormous. The Industrial Revolution demanded better optical instruments for everything from microscopes to lighthouses. Naval warfare required understanding how light traveled across water for signaling. Even early photographers needed to grasp light's properties to capture images. A French naval engineer in 1802 discovered that when designing a lighthouse, wave-based calculations predicted light patterns that reached ships miles further than particle calculations suggested, potentially saving countless lives. What makes this debate fascinating is that both sides approached a truth stranger than either could. Imagine. The resolution would come, but in a way no one expected. Neither side would be completely right or wrong, The answer lay in a reality more bizarre than 17th or 8th century physics could comprehend. The first hints of this strange resolution appeared in 1801 when Thomas Young performed an experiment that seemingly demonstrated light's wave nature. Young, an English physician and physicist, designed a simple but ingenious setup that would become one of scientific history's most famous experiments. The argument between particles and waves represented two fundamentally different ways of understanding physical reality. In the particle view, nature consists of tiny discrete objects interacting through forces. In the wave view, nature consists of continuous fields of energy flowing and interacting. These competing visions drove the debate's intensity. Each theory had its challenges. If light consisted of particles, why didn't light beams bounce off each other when crossing? Particles should collide, but light beams pass through undisturbed. Waves offered an explanation. They can pass through each other, combining temporarily but continuing unchanged afterward. However, the wave theory had its own problems. Waves need a medium. Sound waves move through air, water waves through water. But light traveled through empty space, like the vast distance between sun and earth. What substance could fill the entire universe to carry light waves? The mysterious ether became increasingly problematic as astronomy advanced. The stage was set for Thomas Young to challenge Newton's dominant theory with an experiment so simple yet profound that it would eventually lead physics to quantum mechanics. Young's experiment would demonstrate something particle theorists couldn't explain, that light created interference patterns like waves do. Yet over a century later, physicists would discover that individual particles could somehow create these same patterns, but only when unobserved. This experiment with two simple slits would become the centerpiece of a physics revolution. As we turn to Young's breakthrough, remember that the centuries-old debate wasn't settled by proving one theory right and one wrong, but by transcending both with a new understanding neither Newton nor Huygens could have imagined. Thomas Young's revolutionary experiment. How does a simple experiment with two slits and a light source change our understanding of physics forever? In 1801, a brilliant English scientist named Thomas Young performed what would become one of the most significant experiments in scientific history. One that would challenge the dominant thinking of his time and eventually open the door to the bizarre world of quantum mechanics. Thomas Young, trained as a physician and accomplished across numerous fields from language translation to eye anatomy, had a particular fascination with light and vision that led him to question scientific orthodoxy. At the time, Newton's particle theory of light dominated physics. Few scientists dared challenge Newton's ideas. His reputation was immense, and his contributions to science were foundational. Yet Young found himself unconvinced by certain aspects of the particle theory. He noticed it struggled to explain several optical phenomena, particularly the colorful patterns seen in thin films like soap bubbles. These observations led him to resurrect the wave theory of light that had been largely dismissed during Newton's era. The scientific community of the early 19th century was not receptive to challenges to Newton's ideas. The Royal Society of London, the preeminent scientific organization in Britain, was firmly in the Newtonian camp. Young knew that any challenge to the particle theory would face intense scrutiny and likely rejection. Nevertheless, he designed an experiment elegant in its simplicity. Young's experimental setup was remarkably straightforward. He took a small, bright light source and placed it behind a card with a single, narrow slit. This created a thin beam of light that spread out slightly due to diffraction. This spreading beam then encountered a second card containing two narrow, parallel slits positioned very close together. The light passing through these two slits fell onto a screen some distance away. If light consisted of particles, as Newton claimed, what should happen when these particles encounter two parallel openings? Logic suggested these particles would pass through either one slit or the other and create two bright patches on the screen. But what Young observed instead defied conventional expectation. The screen showed a series of alternating bright and dark bands, an interference pattern. This pattern was the smoking gun that Young had been looking for. He immediately recognized what it meant. The light passing through the two slits was behaving exactly like water waves passing through two openings. When water waves pass through two gaps, they spread out and overlap. In some places, the peaks of both waves align and create a larger wave, constructive interference. In other places, the peak of one wave meets the trough of another, and they cancel each other out, destructive interference. The alternating bright and dark bands on Young's screen corresponded perfectly to this wave interference pattern. The bright bands appeared where light waves constructively interfered, reinforcing each other. The dark bands formed where the waves destructively interfered, canceling each other out. This result couldn't be explained if light consisted of particles traveling in straight lines. When Young presented his findings to the Royal Society in 1803, the reception was chilly. Many scientists were unwilling to accept evidence that contradicted Newton's theories. Some even attacked Young personally, questioning his competence. The scientific establishment was deeply invested in Newtonian physics and resistant to ideas that challenged its foundations. Young persisted, publishing detailed accounts of his experiments and refining his wave theory of light. He showed how it could explain numerous optical phenomena that the particle theory struggled with. Gradually, his ideas gained support, particularly from continental European scientists who were perhaps less beholden to Newton's legacy. The French physicist Augustin-Jean Fresnel built upon Young's work, developing a comprehensive mathematical theory of light as a wave phenomenon. By the mid-19th century, the wave theory of light had become the scientific consensus, and Young's double-slit experiment was recognized as a pivotal demonstration of light's wave nature. But the story of the double-slit experiment was far from over. Its most profound implications remained hidden for over a century. Young's experiment had settled one debate, but planted the seeds for a far more fundamental question about reality itself. If light truly consisted of waves, as Young had shown, then what exactly was waving? Later, scientists discovered that light is actually electromagnetic radiation, waves of electric and magnetic fields that can travel through empty space. James Clerk Maxwell's work on electromagnetism in the 1860s seemed to definitively confirm light's wave nature. But the story took another turn when Einstein proposed in 1905 that light also comes in discrete packets of energy called photons, effectively particles of light. This returned physics to a seemingly contradictory position, light somehow behaving as both a wave and a particle. This duality raised a perplexing question. Could a single particle of light somehow interact with both slits simultaneously? This would be like a baseball passing through two separate doorways at once, a notion that defies our everyday experience of reality. Young's simple experiment had ignited a mystery that would take over a century to fully appreciate. It showed light creating wave interference patterns that particle theory couldn't explain, but it also opened the door to deeper questions about the nature of light and matter that would eventually lead to quantum mechanics. The double-slit experiment would eventually become the centerpiece of quantum physics, demonstrating that all matter exhibits this wave-particle duality. Even more strangely, it would reveal that the act of observation itself somehow affects the behavior of particles in ways that defy our intuitive understanding of reality. For over a century, Young's experiment lay relatively dormant as a scientific tool. Physicists understood its implication for the wave theory of light, but they hadn't yet pushed it to its logical and bizarre conclusion. That would happen in the quantum era, when this simple setup with two slits would reveal the most profound mystery in all of physics. Particles behave differently when we watch them. The quantum twist, one particle at a time. What happens when you perform the double-slit experiment with just one particle at a time? The results defied all logic and forced scientists to question the very nature of reality. The early 20th century marked a period of profound transformation in physics. Einstein had recently published his theories of relativity, revolutionizing our understanding of space, time, and gravity. But another revolution was brewing in the world of the very small. Scientists were encountering phenomena that classical physics simply couldn't explain. The orderly, predictable universe of Newton was giving way to something far stranger. During this period, physicists began revisiting Young's double-slit experiment. The wave theory of light had become well established, but new questions were emerging. Einstein had proposed in 1905 that light also behaves as discrete particles called photons. This suggested a perplexing duality, light somehow acting as both a wave and a particle depending on how you measured it. This wave-particle duality presented a fascinating question. What would happen if you performed a double-slit? Experiment one particle at a time? If light consisted of individual particles, sending them one by one to the apparatus should produce different results than a continuous beam. The interference pattern Young observed seemed to require waves interacting with each other. How could individual particles, separated in time, possibly create the same pattern? In the 1920s, this question moved from theoretical to practical. New technologies allowed scientists to control particles with unprecedented precision. Physicists developed electron guns that could fire individual electrons at a target. These devices used heated filaments to emit electrons that were accelerated through an electric field, similar to old television tube technology. Comparable setups could emit photons using very dim light sources that release particles so infrequently that only one would be present in the apparatus at any time. The experimental setup mirrored Young's original. Scientists created a source emitting single particles, either photons or electrons. These particles traveled toward a barrier with two slits, with a detection screen behind to record where individual particles landed. For electrons, this might be a phosphorescent screen. For photons, they used photographic plates or electronic detectors. Crucially, particles were sent through one at a time, with enough delay between them that no two particles could interact. Classical physics predicted these particles would pass through either one slit or the other, gradually building two distinct bands on the screen. What happened instead astonished everyone. The particles accumulated one by one, slowly, unpredictably. Yet over time, they formed a pattern. Like artists unknowingly contributing to a mural larger than themselves, each particle added a dot to what gradually revealed itself as a perfect interference pattern, identical to what waves passing through both slits would create. This result defied classical explanation. How could a single particle create an interference pattern that required passing through both slits simultaneously? Each particle arrived at a specific point, detected as a discrete entity, yet together they showed wave interference. The implications challenged our most basic understanding of reality. Each individual particle somehow traveled through both slits at once, interfering with itself before appearing at a single point. In 1924, Louis of Broglie proposed that all matter possesses wave-like properties, with wavelengths inversely proportional to momentum, lambda equals hp. This hypothesis unified wave and particle behavior, suggesting all particles exhibit wave characteristics. Experimental confirmation came in 1927 through the Davis and Germer experiment at Bell Labs and Thomson and Reed's work at Cambridge. Both teams observed electrons behaving as waves when scattered through materials. These experiments supported matter's wave-particle duality, but the single-particle double-slit experiment revealed something deeper. It suggested particles exist as probability waves until measured. Each particle doesn't follow a definite path. Instead, it exists in a superposition of states, essentially taking all possible paths simultaneously. This concept of superposition became fundamental to quantum mechanics. In the quantum world, particles don't possess definite properties until measured. Instead, they exist as probability distributions described by their wave function. Scientists struggle to interpret these findings. How could something be both a localized particle and a spread-out wave? The Copenhagen interpretation, developed by Bohr and Heisenberg, suggested focusing only on what we can measure. According to this view, probability waves collapse into definite states upon observation. If particles really go through both slits simultaneously, could we catch them in the act? When scientists placed detectors at the slits to observe which opening each particle passed through, something remarkable happened. The interference pattern vanished. Instead, two distinct clumps appeared, as if particles were indeed tiny bullets passing through one slit or the other. Somehow, the mere act of watching the particles changed their behavior from wave-like to particle-like. This wasn't equipment limitation, it was fundamental to quantum reality. The act of observation itself forced particles to choose a definite path rather than existing in multiple possibilities simultaneously. This phenomenon that particles seem to know they're being watched strikes at the heart of what we consider reality. It leaves even the most rational minds uncomfortable with its implications. How can inanimate particles behave differently when observed? The answer to this question takes us deeper into quantum mechanics mysteries, challenging our most basic assumptions about an objective, independent reality. The observer effect, reality changes when you look. Why does the act of measurement itself completely change the behavior of quantum particles? This question takes us to the heart of quantum weirdness, where reality seems to depend on whether anyone is looking at it. After discovering that single particles somehow create interference patterns as if they're going through both slits at once, scientists naturally wonder what would happen if they tried to catch particles in the act. If an electron or photon really travels through both slits simultaneously, could we observe this bizarre behavior directly? This seemingly innocent question led to one of the most profound discoveries in physics. In the 1970s and 1980s, experimental technology had advanced enough to allow scientists to set up sophisticated versions of the double-slit experiment with particle detectors. These detectors could be placed near the slits to record which opening each particle passed through. The setup seemed straightforward. Send particles one toward the double slits, but this time monitor which slit each one travels through, then observe the pattern that forms on the detection screen. Scientists used various methods to detect the particles' paths. Some experiments used tiny electronic detectors placed directly beside each slit. These detectors could register the electrical charge of passing electrons or the energy of photons without seemingly interfering with their path. Other experiments used more indirect methods, like scattering light off electrons to reveal their position, providing what seemed like a non-invasive way to determine which slit the electron traveled through. The Weizmann Institute of Science conducted one particularly elegant experiment to demonstrate this effect. They built a device less than 1 micron in size with a barrier containing 2 openings. They sent a current of electrons toward the barrier and used a tiny electronic detector to spot passing electrons. By changing the detector's electrical conductivity, they could alter its ability to detect electrons. What happened next shocked the scientific community. When the particles were monitored, the interference pattern completely disappeared from the detection screen. Instead of the alternating bands of light and dark that indicate wave interference, the screen showed just 2 bands of particles directly behind each slit. Exactly what you'd expect if the particles were behaving like ordinary objects traveling through one opening or the other. This result was incredible. The very same experimental setup that produced wave interference when unobserved now produced a completely different result when detectors were added to monitor the particles. The only difference was the act of measurement itself. Somehow, the mere attempt to observe which slit each particle traveled through forced it to behave like an ordinary particle rather than a probability wave. Scientists initially suspected experimental error or some physical disturbance caused by the detectors. Perhaps the measuring devices were physically interfering with the particles, pushing them into classical behavior. But this explanation quickly fell apart as more sophisticated experiments were conducted. The Weizmann experiments revealed something fundamental. The interference pattern's visibility directly corresponded to the detector's sensitivity. As the detector's capacity to detect electrons increased, the interference pattern weakened proportionally. This graduated response demonstrated that measurement itself, rather than physical disruption, was causing the wave-like properties to vanish, like a secret that can't remain hidden once shared. Every experiment confirmed the same result. As soon as particle trajectories were detected, interference disappeared. This wasn't a fluke or an artifact of poor experimental design. It was a fundamental feature of quantum reality. The scientific community met these findings with disbelief and fascination. Here was direct evidence that the observer plays a crucial role in determining the outcome of quantum experiments. The act of measurement wasn't merely revealing a pre-existing reality. It was somehow participating in creating that reality. This discovery challenged our most fundamental assumptions about the objective nature of reality. In our everyday experience, objects exist in definite states regardless of whether anyone is looking at them. We assume that the moon is still there even when nobody is looking at it. But quantum mechanics suggests that at the subatomic level, this basic assumption breaks down. Particles don't seem to have definite properties until they're measured. What happens when we observe which slit a particle travels through? According to quantum mechanics, before measurement, the particle exists in a superposition of states, essentially taking all possible paths simultaneously. Its behavior is governed by a wave function that ascribes the probability of finding it in various locations. This wave function spreads out and passes through both slits, creating an interference pattern. But measurement causes this wave function to collapse. The superposition of possibilities resolves into a single definite state. The particle becomes localized at one slit or the other. With a wave function collapse, there's no longer any possibility for interference between different paths, and the particles create 2 distinct bands instead of an interference pattern. Werner Heisenberg proposed his famous uncertainty principle, stating that certain pairs of properties cannot be precisely measured simultaneously. The more accurately you measure one property, the less accurately you can know the other. Not just a limitation of technology, but a fundamental feature of reality itself. Niels Bohr developed the complementarity principle, suggesting that quantum objects possess complementary properties that cannot be observed simultaneously. Particles can behave as either waves or particles, but not both at the same time, depending on the type of measurement performed. The observer effect implies that what we call reality depends on observation. This challenged the classical view that researchers are detached observers of an objective reality. In quantum mechanics, the observer becomes an active participant in the system being studied. These discoveries raise profound questions. What counts as a measurement? Does it require a conscious observer, or can any physical interaction constitute a measurement? What happens to quantum systems when nobody is looking at them? Do they exist in all possible states simultaneously until observed? The double-slit experiment reveals something profound about reality at its most fundamental level. The universe doesn't consist of tiny objects with definite properties existing independently of observation. It appears to be a web of probabilities that only resolve into definite outcomes when measured. This challenges our understanding of reality and suggests what counts as an observer. Debunking misconceptions. Does human consciousness hold some special power over quantum particles? This idea has captured the imagination of millions, spreading through popular science books, spiritual teachings, and even Hollywood movies. The notion that our minds can directly influence quantum reality sounds magical, like we're wizards casting spells on subatomic particles through sheer observation. This interpretation gained incredible popularity because it connects science with spirituality. Books like The Tao of Physics and The Dancing Wu Li Masters in the 1970s suggested parallels between quantum physics and Eastern mysticism. Films like What the Bleep Do We Know popularized this perspective, reaching mainstream audiences who were captivated by the idea of mind over matter. These works placed human consciousness at the center of reality, suggesting we actively create the physical world through observation. The concept that consciousness causes wave function collapse emerged from discussions around the Copenhagen interpretation of quantum mechanics. When physicists like Niels Bohr and Werner Heisenberg explained measurement phenomena, they used language referencing observers and observation. This terminology, though useful within physics, created confusion when communicated to the public, suggesting that a conscious mind was necessary to cause the transition from quantum probabilities to definite outcomes. This perspective gained further credibility from statements by prominent physicists. John Wheeler proposed a participatory universe concept, suggesting observers are necessary participants in creating reality. Eugene Wigner, a Nobel Prize winner, even proposed that consciousness might be necessary for wave function collapse. Coming from respected scientists, these ideas reinforced the consciousness interpretation. Despite such alluring ideas, experiments have firmly shown that consciousness plays no special role in quantum behavior. Scientists designed tests comparing automated detectors with human observers. If consciousness were truly the key factor, quantum systems should behave differently with human observation versus automated recording. The results were definitive. Automated detectors without human involvement produced exactly the same effects as systems where humans observed the outcomes. The interference pattern disappeared when detectors monitored the slits regardless of whether a person looked at detector readings immediately, later, or never. What mattered was that the information about particle paths was recorded somewhere, not that a conscious mind processed that information. John Doty, a respected physicist known for explaining complex quantum concepts in accessible terms, clarified on Physics Stack Exchange, the concept you're looking for is decoherence. Indeed, it happens whether or not an observer is looking. This statement highlights the core principle. Quantum systems lose their wave-like properties through interaction with their environment, with or without consciousness involved. These experiments revealed that quantum superpositions collapse through any physical interaction that reveals which path, information. The critical factor is whether the interaction leaves a record of the particle state that could determine which path it took. This record doesn't need to be observed to have an effect. It just needs to exist. In the double-slit experiment, if a particle interacts with a detector recording which slit it passed through, the wave function collapses regardless of whether anyone examines the detector's readings. The mere existence of this information in the physical universe causes the collapse. Even extremely subtle interactions trigger this effect. When a photon bounces off an electron, it creates a correlation that can reveal information about the electron's position. This interaction causes the electron to lose its wave-like properties, even if nobody measures the scattered photon. The information exchange itself matters, not whether anyone accessed that information. Quantum decoherence, the process by which quantum systems lose their wave-like properties, happens constantly in nature without conscious observers. When air molecules collide with quantum particles, photons scatter off objects, or thermal vibrations occur in materials, quantum superpositions break down into classical states. None of these processes require conscious mind. If consciousness were necessary for wave function collapse, the universe would be radically different. Quantum systems in deep space would remain in superposition indefinitely. Stars would exist in superpositions until someone observed them. The early universe, before conscious life evolved, would have been a blur of quantum possibilities rather than the structured cosmos cosmology reveals. The distinction between measurement and consciousness is crucial. Measurement refers to any physical interaction revealing information about a quantum system, creating records that persist in the environment. This information spreading causes quantum systems to transition from probabilistic wave-like behavior to definite particle-like behavior. Quantum entanglement helps explain this process. When a quantum particle interacts with another system, they become entangled. Their properties become correlated in ways that can't be described independently. This entanglement spreads to the environment, transferring the information about the particle state and making it impossible for the original quantum superposition to persist. This process, called decoherence, explains why large objects don't exhibit quantum behavior. They're constantly interacting with their environment, which continuously measures their properties through physical interactions. These interactions occur naturally without consciousness. Humans certainly affect quantum outcomes through experimental design and when we observe detector readings. But our consciousness doesn't possess any special power to collapse wave functions that automated detectors lack. Understanding that consciousness isn't a key factor in quantum measurement removes mystical elements from popular explanations while preserving the genuinely mysterious aspects of quantum reality. The quantum world remains strange. Particles exist in superpositions, create interference patterns when unmeasured, and exhibit entanglement across distances. But these phenomena follow physical laws that apply whether or not conscious beings are watching. Quantum superposition, existing in multiple states. How can something exist in multiple states at once until we look at it? This idea sounds impossible in our everyday world, but it's exactly what happens in the quantum realm. This concept, quantum superposition, forms the foundation of quantum mechanics and explains the bizarre behavior we see in experiments like the double-slit test. In our normal experience, objects have clear, definite properties. A coffee mug sits in one spot on your desk, not in multiple places simultaneously. Your car is either parked or moving, not somehow doing both at once. This common sense view works perfectly for the objects we interact with daily. But when scientists examine the microscopic world of atoms and subatomic particles, they discovered a reality that defies our intuition. Quantum superposition means that particles don't exist in a single defined state until they're measured. Instead, they exist as a combination of all possible states at once. A quantum coin exists simultaneously as heads and tails until someone looks at it, like a symphony playing all possible notes until a conductor signals the final chord. This measurable physical phenomenon is observed in laboratories every day. Recall the interference pattern from our double-slit experiment. Now imagine each particle living in a state of endless possibility until observed. This strange concept prompted physicist Erwin Schrödinger to propose his famous thought experiment in 1935. Frustrated by how difficult quantum concepts were to explain, he envisioned a cat in a sealed box with a radioactive atom connected to a poison mechanism. Since radioactive decay is governed by quantum probability, the atom exists in a superposition of both decayed and not decayed states until measured. According to quantum mechanics, the cat would exist in a superposition of being both alive and dead simultaneously until someone opens the box. Only then would the superposition collapse into one definite state. Schrödinger created this deliberately absurd scenario to highlight how quantum behavior seems nonsensical when applied to everyday objects. At the quantum level, particles don't exist as tiny solid objects with fixed properties. They behave more like spread-out waves of probability, described mathematically by the wave function. This mathematical tool tells us the probability of finding a particle in various possible states or locations. An electron's wave function might indicate a 70% chance of finding it in one position and a 30% chance in another. Crucially, this doesn't mean the electron is actually in one place and we just don't know which one. The electron truly exists in both places simultaneously with different probabilities until measurement forces it to choose one location. The wave function contains all information about a quantum system's possible states, evolving smoothly according to Schrödinger's equation. When we measure the system, the spread-out wave function suddenly collapses into a single, definite state. This collapse seems to be a different process entirely, triggered by measurement. The mathematics of wave functions has proven remarkably accurate in predicting experimental results. When scientists calculate how quantum particles should behave using these probability waves, the predictions match real-world measurements with extraordinary precision. These successful predictions confirm that superposition reflects something fundamentally true about reality at the quantum level. Connecting this to the double-slit experiment, when a particle approaches the two slits, its wave function spreads out and passes through both openings simultaneously. The particle exists in a superposition of going through both left and right slits. These possibilities then interfere with each other, creating the distinctive banded pattern on the detection screen. This explains how single particles sent through one by one gradually build up an interference pattern. Each particle exists in superposition as it passes through the slits, interferes with itself, and then collapses to a single position upon detection. The position where each particle lands is random, but collectively they create a pattern reflecting the underlying probability wave. When we place detectors at the slits to observe which path each particle takes, we force the particle to collapse into a definite state before it can pass through both slits. The particle must choose one slit, destroying the possibility for self-interference and eliminating the interference pattern. This happens not because detectors physically disturb the particles, but because measurement itself forces quantum systems to resolve their multiple possibilities. Superposition explains why electrons and atoms exist in electron clouds rather than following precise orbits. It's also why quantum computers show such promise. They can represent multiple states simultaneously, potentially calculating in ways classical computers cannot. While the mathematics describing superposition is well established and experimentally verified, what superposition actually means remains debated. Does the particle literally exist in multiple states, or does superposition simply reflect our limited knowledge? The equations work either way, but the interpretation matters for understanding reality. What makes superposition so difficult to grasp is that it vanishes upon observation. We never see objects in superposition, only the results after superposition has collapsed. It's like studying a dream that disappears the moment you wake to examine it. But if quantum particles exist in superposition until measured, why don't larger objects like cats, people, or planets exist in multiple states simultaneously? Why does our everyday world follow different rules in the quantum world? The answer lies in quantum decoherence, which explains how quantum effects get suppressed in larger systems through countless interactions with their environment. Quantum decoherence, why we don't see quantum effects in daily life. If quantum particles behave so strangely, why don't we see basketballs going through two doors at once? If electrons can exist in multiple places simultaneously, shouldn't larger objects made of electrons show the same bizarre behavior? This apparent disconnect between the quantum world and our everyday experience has puzzled physicists for decades. Quantum mechanics as a universal theory that applies to everything in the universe. The same mathematical rules that govern electrons should, in principle, apply to basketballs, cars, and even people. The equations of quantum mechanics contain no stipulation that these rules only work for small things. The mathematics describing quantum superposition applies to objects of any size. Yet our everyday world appears completely classical. Basketballs always travel through exactly one doorway. Coffee cups don't simultaneously exist on your desk and in the kitchen. People don't suddenly appear on both sides of a wall. The quantum weirdness that dominates the subatomic world seems to vanish at the human scale. Why? The answer lies in quantum decoherence, the process that explains how quantum systems lose their quantum properties through interactions with their environment. Quantum properties in large objects are like delicate whispers drowned out by the thunderous roar of environmental interactions. To understand decoherence, imagine a calm pond with a perfect ripple moving across its surface. This ripple represents the wave function of a quantum particle in superposition, coherent, orderly, and maintaining its pattern. Now imagine it suddenly starts raining heavily. Countless raindrops hit the pond, creating their own ripples that interfere with the original wave. Within seconds, the perfect ripple pattern gets completely lost in the chaos. The original wave still exists, but it's become hopelessly entangled with all the random ripples from the raindrops. This mirrors what happens when a quantum system interacts with its environment. Each interaction with air molecules, photons, or heat vibrations is like a raindrop hitting the pond. These interactions entangle the quantum system with the environment, causing distinctive quantum properties to fade away. When a quantum particle exists in superposition, different components of that superposition maintain specific phase relationships essential for quantum interference effects. When the particle interacts with its environment, information about its state spreads into the surrounding world, destroying those phase relationships and eliminating interference possibilities. Decoherence happens automatically without any conscious observation. When an electron interacts with a nearby air molecule, information about the electron's position gets recorded in the air molecule state. As more particles become entangled with the electron, its quantum information spreads further. From a practical perspective, it now behaves as if it had collapsed into a definite state. The rate of decoherence depends dramatically on an object's size and environment. Consider a basketball approaching two doorways, theoretically in superposition of going through both. That basketball collides with trillions of air molecules every second. These countless interactions cause the basketball's superposition to deco. Here almost immediately, in less than a trillionth of a second. The basketball effectively chooses one door far too quickly for us to ever observe quantum behavior. Physicist Wojciech Zurek formalized much of our understanding of decoherence in the 1970s and 1980s. His work helped solve what physicists call the measurement problem, explaining how quantum systems appear to collapse into definite states during measurement without invoking observers. Zurek showed that environmental interactions alone can explain the emergence of classical behavior from quantum systems. The decoherence timescale shrinks exponentially as objects grow larger. For a dust particle, decoherence happens in microseconds. For a virus, it's nanoseconds. For a basketball, it's virtually instantaneous. This creates a practical divide between quantum and classical worlds, though the underlying physics remains the same. If decoherence happens so quickly, how do scientists study quantum effects at all? Through extreme isolation. Quantum experiments require extraordinary measures to shield particles from their environment. Scientists use ultra-high vacuums to remove air molecules, supercooled environments to minimize thermal vibrations, and sophisticated electromagnetic shielding to block radiation. These precautions temporarily protect quantum states from decoherence, creating windows to observe quantum behavior before it vanishes. Creating these isolated environments has become central to quantum technology development. Quantum computers require qubits to remain in superposition long enough to perform calculations. Engineers have developed systems that can preserve quantum states for milliseconds or even seconds, an eternity in quantum terms, but still incredibly brief by human standards. Decoherence solves a paradox between quantum and classical behavior without requiring new physics or a mysterious role for consciousness. The classical world emerges naturally from the quantum world through unavoidable environmental interactions. This understanding has practical applications. By controlling decoherence, scientists can harness quantum properties for revolutionary technologies. Quantum computers, sensors, and communication systems all depend on our ability to protect quantum states from decoherence long enough to utilize them. The boundary between quantum and classical isn't a fundamental divide in nature. It's a practical limitation created by decoherence. As technology improves, we're pushing this boundary further, creating larger systems that maintain quantum properties longer. This expanding frontier of quantum control advances technology while helping us understand the profound connection between the strange quantum world and the familiar classical reality we experience every day. Quantum technologies, harnessing the observer effect. How are scientists turning the bizarre quantum behaviors we've discussed into technologies that could transform our world? The strange quantum effects that once seemed like scientific curiosities are now the foundation for a technological revolution that's already underway. The journey from theoretical quantum mechanics to practical applications represents one of the most significant shifts in modern science. For decades after the development of quantum theory, these ideas remain largely in the realm of fundamental physics. Scientists discuss wave-particle duality and the observer effect in university classrooms, but these concepts seem disconnected from everyday technology. This changed dramatically toward the end of the 20th century when researchers began to recognize that quantum properties were potential tools that could accomplish tasks impossible for conventional technology. Building quantum technologies presents enormous challenges. The very properties that make quantum systems interesting, superposition, entanglement, and wave-like behavior, are extremely fragile. As we learned in our discussion of quantum decoherence, quantum systems lose their special properties almost instantly when they interact with their environment. This makes creating useful quantum technologies a bit like trying to build a sandcastle while waves constantly wash away your work. Scientists must find ways to protect quantum states long enough to perform useful operations with them. Various approaches have emerged to overcome the decoherence problem. One strategy involves cooling quantum systems to temperatures just above absolute zero, which minimizes thermal vibrations that can disrupt quantum states. Another method uses sophisticated error correction techniques that can detect and fix quantum errors before they destroy the computation. Some systems are designed with inherent resistance to certain types of environmental noise. These protection methods create tiny islands of quantum behavior that can be preserved long enough to be useful. Quantum computing represents perhaps the most revolutionary application of quantum mechanics. Conventional computers process information using bits that can be either 0 or 1. Quantum computers use quantum bits or qubits that can exist in superposition 0 and 1 simultaneously. This fundamentally changes what's possible in computation. A quantum computer with just 300 qubits could represent more combinations of states than there are atoms in the visible universe. This massive parallelism gives quantum computers the potential to solve certain problems far faster than any classical computer ever could. Factoring large numbers, finding which prime numbers multiply together to create a larger number, is extremely difficult for conventional computers. Our modern encryption systems rely on this difficulty to keep data secure. A sufficiently powerful quantum computer could use Shor's algorithm to factor large numbers exponentially faster than the best classical methods, potentially breaking encryption systems that secure everything from banking transactions to military communications. Quantum computers show tremendous promise for simulating quantum systems themselves, which could revolutionize materials science and drug discovery. Developing new medications often requires understanding how molecules interact, a process that involves quantum mechanics. Quantum computers could model these interactions naturally, dramatically accelerating the discovery of new materials or medications that target specific diseases. In 2019, Google announced it had achieved quantum supremacy, performing a calculation on a quantum computer that would be practically impossible for classical supercomputers. While this calculation didn't have practical applications, it represented an important milestone in the field. IBM has made quantum computers available via cloud access, allowing researchers worldwide to experiment with quantum algorithms. Quantum cryptography offers solutions to security challenges created by quantum computing. This technology uses the observer effect to create communication channels that cannot be hacked without detection. If an eavesdropper tries to intercept quantum information being transmitted between two parties, their measurement disturbs the quantum states, alerting the communicators to the intrusion. Quantum key distribution systems are already commercially available and have secured bank transfers and election results in some countries. These systems typically use the polarization states of photons to encode information, making it possible to know if communications have been compromised. Quantum sensing exploits properties like superposition and entanglement to measure physical quantities with unprecedented precision. Atoms in superposition states can be extraordinarily sensitive to external forces. Quantum sensors have already improved the precision of gravitational measurements, magnetic field detection, and atomic clocks. More precise gravitational sensors could improve navigation systems, detect underground structures, or predict volcanic eruptions. Better magnetic field sensors could improve medical imaging techniques like magnetic fields produced by firing neurons. The ability to measure time with greater precision impacts everything from GPS systems to financial trading networks. The global race to develop quantum technologies has intensified with major investments from governments and corporations worldwide. The United States, China, European Union, Japan, and others have launched billion-dollar initiatives to advance quantum technology development. Tech giants like IBM, Google, Microsoft, and Intel have built increasingly powerful quantum computers, while startups focused on specific quantum applications have proliferated. The potential impact of fully realized quantum technologies extends to drug discovery, climate modeling, financial systems, artificial intelligence, and cryptography. Quantum communications could create fundamentally secure networks. Quantum sensors could revolutionize medical diagnosis, geological surveying, and navigation systems. The development of quantum technologies forces us to confront the philosophical implications of quantum mechanics in tangible ways. As one researcher noted, we've essentially unlocked a new dimension for exploring and manipulating this phenomenon, and we're only beginning to scratch the surface. When we build machines that directly harness quantum superposition
Einstein's
and
objections.
entanglement,
God
we're
doesn't
testing
play
our
dice.
understanding of
Why
reality
did one of
itself.
history's
Greatest minds reject the theory he helped create? Einstein's relationship with quantum mechanics represents one of the most fascinating scientific disagreements in history. While he contributed fundamentally to quantum theory's early development, Einstein spent the last decades of his life arguing against its most basic implications. Einstein's contributions to quantum physics were pivotal. His work on the photoelectric effect, showing that light comes in discrete packets called photons, helped establish quantum physics, earning him the Nobel Prize. Yet as quantum theory evolved in the 1920s and 1930s, Einstein became increasingly uncomfortable with its direction. At the heart of Einstein's objection was a profound philosophical difference about how the universe operates. Einstein believed in a deterministic reality, a universe where every effect has a definite cause, where nothing happens randomly, and where the fundamental laws of physics always produce predictable outcomes given sufficient information. This view reflected his deep intuition about nature's order and elegance. Einstein saw the universe as inherently logical and comprehensible. Quantum mechanics painted a radically different picture. In the quantum world, particles don't have definite positions or momentums until measured. Their properties exist as probabilities, not certainties. When scientists measure quantum systems, they get random results governed only by probability distributions. This inherent randomness troubled Einstein deeply. This philosophical divide crystallized in Einstein's famous quote, "God does not play dice with the universe." This metaphor expressed Einstein's conviction that randomness couldn't be a fundamental feature of reality. During heated debates with other physicists, Einstein would use this phrase to emphasize his belief that if quantum mechanics relied on probabilities, it must be incomplete, a useful approximation missing deeper, deterministic laws beneath the surface. The most significant debates occurred between Einstein and Niels Bohr, the primary architect of the Copenhagen interpretation of quantum mechanics. Their discussions, conducted at international physics conferences during the 1920s and 1930s, shaped how scientists understood quantum theory. These weren't technical disagreements alone. They represented fundamentally different philosophical approaches to science itself. Bohr embraced quantum mechanics' probabilistic nature, arguing that we should focus on measurements rather than speculating about an unobservable reality. Einstein insisted that a complete theory should describe objective reality existing independently of measurement. Their debate centered on thought experiments Einstein devised to expose what he saw as contradictions in quantum theory. Einstein would propose situations where quantum mechanics seemed to lead to paradoxes, and Bohr would resolve them within quantum theory's framework. Repeatedly, Bohr answered Einstein's challenges, though never fully convincing him. In 1935, Einstein launched his strongest attack on quantum mechanics. With colleagues Boris Podolsky and Nathan Rosen, he published a paper presenting the EPR paradox. This thought experiment involved entangled particles whose properties remain connected regardless of distance. Einstein argued this entanglement created a contradiction. Either information traveled faster than light, violating relativity, or quantum mechanics was incomplete because it failed to account for predetermined values. This paper formalized Einstein's belief that quantum mechanics must be missing hidden variables, underlying deterministic mechanisms explaining apparently random quantum behavior. In Einstein's view, quantum randomness wasn't truly random, but reflected our ignorance of these hidden processes. For years, the EPR paradox remained philosophical rather than experimental. In 1964, physicist John Bell developed a mathematical theorem to test Einstein's hidden variables idea. Bell showed that if Einstein was right, certain measurements on entangled particles would produce results within specific statistical limits. If quantum mechanics was correct, those limits would be exceeded. When scientists conducted these experiments in the 1970s and 1980s, the results decisively supported quantum mechanics. The experiments, particularly by a land aspect, showed entangled particles exhibited correlations stronger than any hidden variable theory could explain. Einstein's objections, though philosophically sophisticated, were contradicted by experimental evidence. These experiments confirmed quantum non-locality, entangled particles influencing each other instantaneously across any distance. Einstein had called this spooky action at a distance and considered it impossible. Yet experiments repeatedly confirmed this as a genuine feature of our universe. Einstein died in 1955 before these experimental tests. He never abandoned his conviction that quantum mechanics was incomplete. What would he think about Bell's inequality experiments? Given Einstein's respect for evidence, he might have reconsidered his position, though perhaps finding another angle to question these results. Einstein's objections to quantum mechanics weren't the complaints of a physicist unable to accept new ideas. They represented profound questions about reality, causality, and scientific explanation that continue to resonate today. Even as experiments confirm quantum mechanics predictions, Einstein's questions about what quantum mechanics means for our understanding of reality remain relevant. The Einstein board debate represents something valuable in science, a disagreement between brilliant minds that push both to sharpen their thinking. Einstein's commitment to a comprehensible universe governed by rational laws drove him to question quantum theory in ways that ultimately strengthened it. Today, as we develop technologies harnessing quantum phenomena, we're building tools based on principles Einstein questioned. Yet his philosophical inquiries about reality and scientific theories continue to inspire new interpretations of quantum mechanics, continuing the conversation Einstein started nearly a century ago. Quantum reality challenging our understanding of existence. What does quantum mechanics tell us about the nature of reality itself? This question takes us beyond the mathematics and experiments to the heart of what existence means. After a century of quantum discoveries, physicists debate what quantum mechanics actually says about the world we live in. The equations work perfectly to predict experimental results, but their meaning remains controversial. When scientists confront the strange results of quantum experiments, they naturally try to make sense of them. This has led to multiple interpretations of quantum mechanics, different ways of explaining what's really happening when particles pass through both slits simultaneously or change behavior when observed. Each interpretation offers a different vision of reality, and none has been definitively proven right or wrong because they all make the same experimental predictions. Let's start with the most widely accepted view, the Copenhagen interpretation. Developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, this approach served as the standard understanding of quantum mechanics for decades. According to this interpretation, quantum systems exist in superpositions of multiple states until measured, at which point the wave function collapses into a single definite outcome. The Copenhagen interpretation doesn't try to describe what's happening between measurements. It focuses instead on what we can observe and measure. This approach emphasizes a shut up and calculate philosophy, use the equations to predict experimental results rather than worrying about underlying reality. The Copenhagen view holds that classical concepts like position and momentum only become meaningful through the act of measurement. This interpretation assigns a central role for observation in quantum mechanics. It proposes that physical properties don't exist in a defined state until measured. The wave function represents our knowledge about possible measurement outcomes rather than a physical entity. This raises profound questions. Is reality created through observation rather than simply revealed by it? The Copenhagen interpretation struggles to clearly define what constitutes a measurement and relies on wave function collapse without explaining the mechanism. Like a magician who pulls a rabbit from a hat without revealing the trick, Copenhagen acknowledges the outcome without explaining the process. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a dramatically different approach. While Copenhagen suggests wave functions collapse upon measurement, many worlds proposes the wave function never collapses. Instead, every possible outcome occurs, each in its own parallel universe. When an electron passes through the double-slit apparatus, it truly passes through both slits, but in different branches of reality that separate from each other. According to many worlds, measurement causes the universe to split into multiple versions, one for each possible outcome. In one universe, you observe the electron going through the left slit. In another, an identical version of you observes it going through the right slit. These universes evolve independently, unaware of each other's existence. This interpretation eliminates wave function collapse and the special observer rule. It provides a deterministic view where everything possible happens somewhere. The mathematics remains identical, but the implied reality features countless parallel universes constantly branching from each other. Key differences: Copenhagen, reality, undefined until measured. Wave function collapses, many worlds, all possibilities realized in parallel universes. No collapse needed observer rule. Central in Copenhagen, incidental in many worlds. Quantum Bayesianism approaches the problem from a third angle. While Copenhagen sees quantum states as physical systems, and many worlds sees them as objective realities, QBism views quantum states as representing an observer's knowledge and beliefs. Quantum states don't describe what exists, but what an agent knows about potential future experiments. In this view, the wave function exists as a mathematical tool for predictions based on current knowledge. Probabilities represent degrees of belief rather than frequencies or randomness. When we measure a quantum system, we're simply updating our knowledge. QBism reframes the observer affect as a reflection of changing beliefs based on new information. This aligns quantum mechanics with science as describing personal experience rather than objective reality. These interpretations reveal something important about quantum mechanics. It tells us what we'll observe in experiments, but not necessarily what reality is. The mathematics works perfectly, yet translating equations into a coherent picture of reality remains challenging, like trying to understand a foreign culture through dictionary definitions without experiencing the culture itself. The interpretations challenge our basic assumptions about existence. Is reality objective and independent of observation? Does observation determine what's real? Do all possible outcomes happen in parallel universes? Are quantum states merely representations of knowledge rather than physical reality? The observer effect raises particularly profound questions. If observing a particle changes its behavior, the line between observer and observed blurs. We can no longer see ourselves as passive spectators of an independent reality. On some level, our interactions with the world help shape what that world becomes. The implications extend to causality and determinism. The uncertainty principle suggests an inherent indeterminism in nature, challenging the classical notion that the present completely determines the future. This raises questions about free will, causality, and the nature of time itself. Quantum mechanics suggests the universe differs fundamentally from our intuitions. The solid, definite world of experience might emerge from a deeper reality of probabilities and interconnections. Objects might lack definite properties until they interact with other systems. Reality might be participatory rather than simply waiting to be discovered. These philosophical questions remain open. Science has given us remarkable mathematical tools for predicting quantum behavior, but their meaning for our understanding of reality continues to challenge our deepest intuitions about existence. The double-slit experiment shows us something remarkable. Reality at its core behaves nothing like our everyday experience suggests. What we consider solid and predictable emerges from a quantum world that follows entirely different rules. As we build quantum computers and develop new technologies based on these principles, we're testing the boundaries of reality itself, forcing us to question fundamental concepts like observation and existence. With each new experiment, the mystery deepens. Quantum physics fascinates through the profound questions it raises about our universe. What does it mean for you when reality